Hi, in this video we're going to be talking about general solutions. So we decided to make the video based on the fact that our students were finally grasping the idea, but we had realized that many students are actually struggling to understand what is general solution and why is it so important in mathematics. So we are going to take a look at a general review of what is expected to be known. So this one will be very suitable for grade 11 and grade 12 learners. For grade 10, we were expected to know how to sketch the trigonometric graphs, the basic trigonometric graphs with a bit of shifting here and there and amplitude changes. But we are going to start with the basic sine graph. It's done as an example. It could have been done as a cos graph, tan graph, or any other graph that we've done in trigonometry. So, in sketching the sine graph, of course, you can use your calculator to check the values, the key values of the function, but generally this is the shape that you should be having, which is wavy. Now, just take note that as much as in grade 10, we were learning to sketch from 0 to 360. So we had the sketching done from 0 degrees to 360 degrees. And then we were able to get the wave in the shape that we have it on the board. Now we are extending it to negative 360. Without losing generality, we need to understand that this graph can actually continue on forever. This has an infinite domain, which means that any number that you put, as long as it's a real number, you will get an answer in the sine graph. So let's go back to what is general solution. So in grade 10, we were studying solve for x questions in trigonometry. The method there was, if you have sine x equals to half, you are able to get the x value by taking sine to the other side and it becomes the inverse of it, or sine to the negative 1. So this inverse sine of half, when you punch it in your calculator using shift and then the trigonometric function button for sine, you are able to get 30 degrees. This will always happen on your calculator. It will always give you 30 degrees because the calculator always gives us the acute angle for these positive gradients of numbers. Therefore, we then go back and look at the following fact. If you go back to your calculator and check sine of 390, you will find that it also gives you this exact number. So now we are seeing there's a problem in our solution. We got 30, but 390 is also a solution. It doesn't end there. You put 750, you get a half. You put negative 330, you get a half. You put 150, you get a half. I can continue on like this, listing the numbers forever because there are infinitely many of them. So where is this coming from? This is coming from, we are trying to find out, as the graph is going up and down, up and down, up and down, at which points is it touching the y value of half or 0.5. So we can already see that on this graph that I've sketched, there are 5 points given. So this answer that we got actually corresponds to this answer here, which is 30 degrees. Then this one here of negative 330 is the one for here, and then there are a few others that were not listed, but the 150 is also here, and so forth. 390 coming up over here. So the problem has been made clear that what we get from the calculator by doing sine inverse half, which is 30 degrees, is not the full solution. Therefore, we need a better way of representing all of these solutions, and that will be resting on two things. Sine has a period of 360. It means that it takes 360 for a full wave to be formed. So that's what period is. So therefore, since a full wave is formed at 360, it means that if you keep adding 360 to this number, no matter how many 360s you add, the answer you get will definitely be a solution to this problem here. So now that brings us to the first one. The second case is, we also have this fact over here that tells us, it's also referred to as the cast method, that tells us that sine is actually achieving two values that are equal while going up and while coming back down, which is in the second quadrant when it comes back down for the first case. Therefore, sign is positive in the first and second quadrant. So that means that we have two sets of solution. The first one is the set of solution from the first quadrant. Now that one can be represented as x is equals to 30 degrees, which is the answer that we got from there, plus k times 360 degrees. Now, we need to explain what is this k. The question never spoke of any k. So we are introducing a k that we need to explain what it is as a function. So the k must be any multiple of 360. That means that it can be 1, 2, 3, 4, 5, 6, and even the negative multiples. Negative 1, negative 2, negative 3, negative 4. So this here, integers, means it can be 0, it can be 1, it can be negative 1, it can be 2, it can be negative 2. That can go on forever, that can go on forever. No matter which number you have, you will be able to get that. As an example, for this one here, this is the k is 2 case. So we have 330 plus k times 360, where k is now made to be 2 times 360. I don't need to mention that because now we have a number. So we have 330 plus 720 degrees. BODMAS, multiplication first before addition. Therefore, we have 750 is definitely a solution. We can continue doing these things. For example, if I change this around, making k 3. This gives me 1080 degrees, which means that now the answer would be 1110 degrees. Try that one, take it, put it in the x or here, then you will see that it also gives you the answer. So as long as the k is changing as these numbers here, we are definitely having a solution giving half. Therefore, we are not done, because whatever you do here as k values, the 150 would never come up. So what do? We then have to consider that the 150 actually came from the second quadrant. All of these ones that were written here are from the first quadrant, because we say that if you are moving from 30, then you do a full 360 rotation, you're coming back to the same point. Another 360 rotation, same point. So no matter how many rotations you do, you're going to go back to the same point. Now, let's look at the second solution. The second solution would be x is equals to, so second quadrant angles are represented as 180 degrees minus our reference angle of 30. Therefore, we also have multiples of that, of 360 added to that, giving us k element of integers as our variable here. Therefore, the final answer would be 150 plus k times 360 degrees, where k is an element of integers. Of course, it makes better sense for the multiplication to be shown here. Alright, so you can also try changing the values of k. Doesn't matter what number you've put, whether you put 5 billion, 3 million, 6 million, doesn't matter. Just to prove to yourself that there are infinitely many solutions to this, as long as you are maintaining your k as an element of integers. So you can go ahead and try and put a number that's not an integer here, say 0.3, then you will see that the answer that comes out in total will not be a solution to this over here. So that is pretty much what general solution is. We will go on and you can do some exercises. One of the exercises I recommend after here is that you can do the exercise of looking at solve for x. So we will be solving for x for cos x equals 2 root 3 over 2. Then you can also do sine x equals to 1 over root 2, or because of your calculator, let's do it as root 2 over 2. Then you can do these two as an example so that you can see where the basic general solution is. In the later questions, we are then going to do the more challenging ones for grade 11 and 12, which incorporate things like change of the period, factorization before we can actually get to these kinds of places, and we have other things of fraction, multiplication, and division. But we'll do that in another time. For now, this is what general solution is. So it's a very elegant way of writing infinitely many solutions of the question of solve for x with trigonometric functions. It works with all of them, cos, tan, and sine. But in the cos case, it will have exactly the same period as sine. However, tan has a period of 180. So when we get to this section here, we need to put 180 for tan, but we'll do it in another exercise or so. Thank you.